Hello everyone, we are from Group 1. Today we're gonna present about Fourier analysis with application to music. Being with synopsis, the DST is a method that helps us understand digital signals by breaking them down into their individual frequency components. It's commonly used by mathematicians, engineers, and scientists to analyze and process digital signals. This paper explains how the DST works by building on basic calculus concepts, and then show how it can be used to analyze musician signal from chord structure. Second, introduction to music theory. 2.1 Pitch and scale. The perception of a sound wave at a specific frequency is known as pitch. This is picture of chromatic scale. A chromatic scale being an ending at C. 2.2 Triad and chord. A chord is a combination of multiple pitch played simultaneously and is important in music analysis as it describes the melodic and harmonic structure of a section of music. These triads are used to describe two chords in the model. Triad in the key of C. 2.3 Chord inversion. The summary explains that there are 7 chord families and 21 roots, resulting in 147 possible chords. An example of a chord inversion is shown in the picture. Root position, first inversion and second inversion triad in the key of C. 2.4 Two-word chord detection, a chord recognition model developed by Shea and Ellis in 2003, which consists of two major components, signal analysis and chord fitting. The signal analysis component uses the fast Fourier transform to decompose the raw audio signal into chroma intensity, which are then transformed into octave-independent chroma information known as the pitch chord profile.
The introduction to the Fourier transform. Frequency and time domains. The Fourier transform was developed to solve problems in the physics related to conduction of heat in solid and the motion of a puck string. The Fourier transform is invertible, with the inverse Fourier transform returning to the time domain function from a frequency domain function, and it is the graph of frequency and the time domains. The continuous Fourier transform. We first define omega k as the angular frequency. Then the relationship between the time domain function and its corresponding frequency domain function is defined by the below equation. Note the present sinusoidal component within the complex exponential. From first equation, we can derive the inverse Fourier transform. The discrete Fourier transform. Motivated by the continuous case, we write function n to denote nth entry of the vector f. Likewise, the inverse discrete Fourier transform has the form like the below equation. The sinusoid. We define a sinusoid as a function of the form xt equal to a sine 2 pi omega t plus phi. A is amplitude, omega is radiant frequency, 2 pi omega is frequency, t is time, phi is initial phase, 2 pi omega t plus phi is instantaneous phase. Fourier transforms are built on the complex property of sinusoid, which follow from Euler laws. Delta function or direct delta function. First, the delta function is 0 at every point except t0. Second, the area under the delta function is defined to be 1. This property can be exploited to reveal the useful general shifting property to discretize integrals. So this is the method of the Fourier transform of delta function. And the last, we got the two equations on the right hand side.
Number 4, a derivation of the discrete Fourier transform. 4.1, a spike train is a collection of spikes, which are represented by the delta functions in the context of the discrete Fourier transform. The spikes in the spike train are equally spaced in time with a fixed spacing of delta t. Then 4.2, reciprocity relation of the discrete Fourier transform. To discover the reciprocity relation, we will utilize the same sequence in the time domain. Then we got this relation. We now have the tools necessary to derive the precise form of the DFT. In 4.3, the discrete Fourier transform. We will use this solution to find the formula which can employ to analyze the music. And then continuing with the spectrograms and chromograms. Top is a spectrogram and bottom is chromogram. It's clearly that the chromogram is accurately describing the pitch characteristic of chromatic scale, and we have the first step in our chord detection model. Lastly, conclusion. In this paper, we have established a basic understanding of the mathematical concepts underlying a chord recognition model. We have discussed fundamental music knowledge and introduced a contemporary method for chord recognition. Additionally, we have explained the derivation of the discrete Fourier transform from the Fourier transform and highlights the applications of Fourier analysis in signal processing. Lastly, we have illustrated with examples how the fast Fourier transform can be used to create a chromogram from an audio file. Next is our member groups. Thanks for watching and listening.